Tonight, we're going to travel somewhere most people have never truly imagined. Not to a star, not to a distant galaxy. Tonight, we're going to travel into the space between things, into the silence between the stars, into the vast, dark, almost incomprehensible emptiness that makes up nearly everything that exists. And by the end of tonight, you're going to understand exactly why the universe, a place containing 2 trillion galaxies, billions of trillions of stars, and 13.8 billion years of creation, is, at its heart, almost completely, terrifyingly, beautifully nothing. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Here is the question that has quietly haunted astronomers, philosophers, and anyone who has ever lain on their back on a clear night and looked up. If the universe contains so much, so many stars burning so furiously, so many worlds spinning in the dark, so many forces pulling and pushing and shaping everything we can see, then why does it feel so profoundly, so completely, so almost personally empty? Why, when you look between the stars, is there nothing there? Not thin air, not cold fog, not even silence in any sense we understand. Just an absence so total, it has no name in any human language that truly captures it. That is what we are going to sit with tonight, together, in the quiet. Now let's begin. Think about the last time you looked up at the night sky. Really looked. Not a glance through a car window, not a distracted moment between tasks, but a long, slow, deliberate look upward into the dark. If you have ever done that, if you have ever stood outside on a clear night far from city lights and let your eyes adjust until the stars multiplied and the Milky Way stretched overhead like a river of ancient light, then you already know the feeling I want to start with tonight. It is a feeling of fullness, of abundance, of a sky so packed with light that the darkness between the stars almost seems like an afterthought. That feeling is real. And tonight, I am going to tell you why it is also, in a very precise and measurable way, almost entirely wrong. The universe is not full. That is the central, quietly astonishing truth we are going to sit with tonight. Despite everything you see when you look up, despite the 2 trillion galaxies astronomers have now counted, despite the billions of trillions of stars burning inside those galaxies, despite 13.8 billion years of matter clumping and collapsing and igniting and exploding and building, despite all of that, the universe is, by almost any meaningful measure, essentially empty. Not mostly empty the way a room feels empty when only a few people are standing in it. Not empty the way a desert feels empty when you cannot see another person for miles. Empty in a way that has no comfortable human comparison. Empty in a way that, once you truly understand it, changes how you see everything, including yourself. Here is the thing most people do not realize. When we look at the night sky and feel that sense of cosmic abundance, we are being deceived by our own smallness. We are standing on a tiny rock looking out through a thin layer of atmosphere, and we are interpreting the light of objects so distant that their separation from each other, and from us, is so vast it simply does not register in any intuitive way. Our brains were not built for these distances. Our brains were built to track prey across a savanna, to judge the distance to the next tree branch, to navigate the few dozen miles of landscape that mattered to our ancestors. The scale of the cosmos is not something we were ever meant to feel in our bones. And so we look up and we see light and we think full. But the truth is something else entirely. The truth is terrifying, and it is wonderful, and tonight we're going to walk through it together. Let me give you your first number of the evening, because numbers are the only tool we have for cracking open a universe this large. The nearest star to our Sun, the closest stellar neighbour we have, a dim red dwarf called Proxima Centauri, is approximately 4.2 light-years away. 4.2 light-years. That means that light, travelling at roughly 186,000 miles per second, the fastest anything in the universe can move, takes 4.2 years to make that journey. In miles, that distance is approximately 25 trillion miles. 25 trillion, and that is our nearest neighbour. That is the shortest gap between our star and any other star. And in that 25 trillion miles of space between us and Proxima Centauri, there is, for all practical purposes, absolutely nothing. A handful of hydrogen atoms per cubic meter, a temperature hovering just a few degrees above absolute zero, no sound, no warmth, no light bright enough to navigate by, just an ocean of dark, cold, silent nothing, stretching on for 2 decades of travel even if you moved at the speed of light. And here is where it starts to feel genuinely strange, if you let it. Because that gap, that 25 trillion mile corridor of near-perfect emptiness, is not exceptional. It is not some unusual stretch of particularly vacant space. It is typical. It is what space is almost everywhere. In fact, the regions of the universe where matter actually exists in any meaningful concentration, stars, planets, nebulae, the gas clouds between galaxies, those regions are the exceptions. They are the anomalies. The rule, the overwhelming statistical reality of the cosmos, is void. The rule is nothing. Matter, as we know it, as we are made of it, as we depend on it for every breath and heartbeat, is a vanishingly rare phenomenon in a universe that vastly prefers emptiness. This is not a poetic exaggeration. It is a measurable, quantifiable fact. If you were to take all the matter in the observable universe, every star, every planet, every atom of gas and dust and ice, every black hole, every neutron star, every grain of interstellar debris, and spread it evenly across the volume of the observable universe, the average density would be roughly equivalent to a single hydrogen atom spread across a volume about the size of 3 cubic meters. One atom, in a box the size of a large wardrobe, everywhere, in every direction, as far as physics can measure and theory can reach. That is what space on average contains. That is the universe's default state. And yet we exist. You are here, listening to this. Your body built from billions of trillions of atoms arranged in structures of almost incomprehensible complexity. Stars burn, galaxies spin, gravity sculpts enormous structures from the thinnest imaginable raw material. Something, a series of forces and fluctuations and accidents so improbable they border on the miraculous, conspire to take that near-total emptiness and fold it, here and there, into the world you know, into oceans and mountains and nervous systems and music, into the particular configuration of matter that is right now, lying in the dark, listening to the sound of someone's voice describe the void. That paradox, abundance rising from almost total emptiness, is what tonight is really about. It is not just a question about outer space, it is a question about why anything exists at all, why the universe chose, however narrowly, however improbably, to be something rather than nothing. We're going to travel through scales of emptiness tonight. We're going to start close, in our own solar system, and work our way outward, step by step, until the emptiness becomes so vast that the only honest response is a kind of quiet wonder. We're going to look at what fills the universe when matter does not, which turns out to be something stranger and more unsettling than empty space. And we are going to end, as I hope you will end this night, with a feeling not of smallness or dread, but of something rarer and more sustaining, a feeling of belonging to something that, against all odds, exists. There is something I want you to do right now, if you can. I want you to close your eyes for a moment and picture the night sky as you know it. Not the daytime blue, not a cloudy evening, but a truly clear night, somewhere away from the orange glow of streetlights and buildings. Picture it as dark as it gets. Let the stars appear, one by one at first, then dozens, then hundreds, spreading across the dome of your imagination until the whole sky is peppered with light. Hold that image, because what you are picturing right now, that dense, glittering, almost crowded canopy of stars, is one of the most beautiful illusions the human mind has ever constructed. And tonight, gently, we're going to take it apart. The human eye is a remarkable instrument, but it was not designed for honesty about the cosmos. It was designed for survival. It is exquisitely sensitive to light, capable of detecting the glow of a candle flame from nearly 30 miles away on a clear night. And when it looks up at the sky, it does something deeply misleading. It flattens everything. It takes objects that are separated from each other by distances of trillions upon trillions of miles, and projects them all onto the same imaginary dome overhead, as if they were beads pinned to a single sheet of black velvet. Proxima Centauri and a star 10,000 light-years beyond it appear to your eye as two dots of similar size, side by side, perhaps a finger's width apart. The canyon of emptiness between them, unfathomably deep, cold, and silent beyond description, is rendered completely invisible. Your eye shows you the stars, it hides the void. When ancient humans looked up and saw patterns in those lights, bears and hunters and rivers and scorpions, they were doing something natural and intelligent for their circumstances, grouping, connecting, finding meaning in the scatter. The constellations we still use today are inherited from those early attempts to make sense of an overwhelming sky. But the constellations are, from a cosmic standpoint, completely fictional. The stars that form Orion, for instance, are not neighbours. They have no relationship to one another in space whatsoever. Betelgeuse, the red supergiant that forms one of Orion's shoulders, sits roughly 700 light-years from Earth. Rigel, the bright star at Orion's foot, is approximately 860 light-years away. The other stars of the constellation are scattered at various other distances, some closer, some farther, none of them anywhere near each other in the actual three-dimensional structure of the galaxy. Orion is a picture drawn on a window. The landscape beyond the glass is something else entirely. Here is a way to feel this, rather than just understand it intellectually. Imagine you're in an enormous dark room, a room the size of a continent, stretching from here to the horizon in every direction. In this room there are a handful of candles, maybe one every few miles, burning quietly in the dark. You're standing near one of them, and its light illuminates just the few feet around you. Now imagine looking across that room and seeing, in the far distance, the faint glow of another candle, and beyond it, even fainter, another. They look like dots of light in the darkness, close together from your perspective, because you cannot perceive the miles of empty air between them. That is what you are doing every time you look at the night sky. You're seeing the candles, you're not seeing the room, and the room, the space between those candles, is almost incomprehensibly larger than the candles themselves. Let me give you a sense of what the sky would look like if you could somehow perceive true cosmic distances. If you could see not just where the stars are in angle and brightness, but where they actually sit in three-dimensional space, the night sky would transform entirely. Many of the stars you think of as neighbours would drift apart into isolated distant points of light, separated by gulfs so vast you would struggle to draw a line between them. The sense of a busy, populated sky would dissolve almost immediately. What you would see instead, what the sky truly looks like from a perspective that accounts for depth, is a scattering of lonely fires burning at enormous intervals from one another, each one surrounded by its own immense bubble of near-perfect emptiness. The sky is not a tapestry of stars. It is an ocean of nothing, with a few rare, burning islands scattered across it, at intervals that dwarf any distance we have words for. And this is just our immediate galactic neighbourhood. This is the Milky Way, our home galaxy, which is itself a structure roughly 100,000 light-years across. Within that structure, there are somewhere between 100 billion and 400 billion stars. That sounds like an enormous number, and it is. But spread across a disk 100,000 light-years wide and several thousand light-years thick, those hundreds of billions of stars still manage to leave the vast majority of the galaxy as empty space. The average distance between star systems in our galaxy is roughly 5 light-years. 5 light-years of void between each fire. When you zoom out far enough to see the galaxy as a whole, it looks dense, swirling, packed with light. Zoom back in to any particular region of it, and you are back in the dark ocean, surrounded by emptiness in every direction, with the nearest neighbour still impossibly far away. This is the first layer of the illusion, and it is worth sitting with for a moment before we go further. What feels like a full sky is actually a nearly empty one. What feels like proximity, those stars scattered across the dome of the night, apparently close enough that ancient people named groups of them as single figures, is actually an almost incomprehensible separation. The stars are lonely in ways that have no human equivalent. They do not cluster warmly together. They do not drift close enough to light each other's darkness. They burn, each one, in its own private ocean of void, sending light outward in all directions, and that light travels for years, for decades, for centuries before it encounters so much as another atom of meaningful density. The night sky, as beautiful as it is not a picture of abundance. It is a picture of extraordinary, almost total isolation, lit up just enough by rare and improbable fires that we can mistake it, from our small and fortunate vantage point, for something approaching fullness. But here is what makes this more than just a humbling thought experiment. What we have been talking about so far, the visible stars, the distances between them, the flatness of our night sky perspective, this is only the beginning. Because we have not yet talked about what fills the universe beyond the stars we can see. We have not yet talked about what lies in the spaces between galaxies, in the voids between galactic clusters, in the deep structure of the cosmos that even our best telescopes can only partially illuminate. We have not yet talked about what fills most of the universe, which turns out, strangely and disturbingly, not to be anything we can see at all. That is where we are going next. And I promise you, the further out we travel, the quieter and stranger it gets. One of the most honest things I can tell you tonight is that the human brain is simply not equipped to feel the scale of the universe. We can understand it mathematically. We can write the numbers down, perform the calculations, confirm the results with instruments far more precise than our senses. But to genuinely feel the distances involved, to carry them in your body the way you feel the distance between two cities when you drive between them, that is something no human being has ever been able to do. Not astronomers, not physicists, not the men and women who have dedicated their entire lives to studying the cosmos. The numbers are so large they stop feeling like numbers at all and start feeling like sounds. Just syllables, just shapes on a page that the mind reads and then quietly, inevitably, sets aside. Tonight I want to try something different. Tonight I want to build the scale slowly, carefully, using comparisons your body can understand, until the emptiness we are talking about stops being abstract and starts being something you can almost touch. Let us begin close to home. Our sun, the star at the centre of our solar system, the fire that lights our days and warms our oceans and makes all life on this planet possible, has a diameter of roughly 865,000 miles. That is 109 times the diameter of Earth. If the sun were hollow, you could fit approximately 1,300,000 Earths inside it. It is, by any standard we use in daily life, an almost unimaginably large object, and yet in cosmic terms it is thoroughly average. It is a medium-sized star, unremarkable in brightness, middling in temperature, neither the largest nor the smallest, neither the hottest nor the coolest. The sun is ordinary. And if the sun is ordinary, then the distances it sits within are extraordinary in a way that requires a moment of careful preparation before we attempt to cross them. Here is the analogy I want you to hold on to. Imagine we shrink the sun down to the size of a grapefruit, a small round citrus fruit sitting on a table in front of you. At that scale, the Earth would be a grain of sand, roughly 1 millimeter across, orbiting the grapefruit at a distance of about 15 meters. 15 meters. You would need to walk to the other end of a large room just to find our planet. Now, still at this same scale, let us find Mercury, the planet closest to the Sun. It would orbit at about 6 meters from the grapefruit. Mars would be roughly 23 meters out. Jupiter, the largest planet in the solar system, the giant that contains more mass than all the other planets combined, would be a small marble orbiting our grapefruit sun at a distance of about 78 meters. Almost the length of a football field away, and Saturn, with all its magnificent rings, would sit at roughly 140 meters. You would have left the building by now. You would be standing in the street looking back at a grapefruit on a table somewhere inside, with a sequence of grains of sand and small marbles floating between you and it, all of them separated by vast stretches of absolutely nothing. And now, still holding that model in your mind, let us find the nearest star, Proxima Centauri, our closest stellar neighbour. In this scale model, where the sun is a grapefruit sitting on a table, Proxima Centauri would be another grapefruit located approximately 4,000 kilometres away. 4,000 kilometres. At grapefruit sun scale, the nearest star is as far from us as the distance from Madrid to the middle of the Atlantic Ocean. And between our grapefruit and that distant other grapefruit, in that 4,000 kilometre stretch, you would find almost nothing. A few stray particles, a temperature just barely above the coldest cold that physics permits. Not air, not fog, not the comfortable emptiness of a clear sky on a summer day. Something far more total and far more strange. A vacuum so complete it would kill you instantly and without drama, leaving no trace of your presence in a void that was old before the Earth existed. Now here is where this stops being merely interesting and starts being genuinely, quietly terrifying. Because the solar system we just modelled, that grapefruit and its distant grains of sand, is not a particularly empty system by cosmic standards. Our sun has planets. Many star systems have no planets at all, or have planets so hostile to any form of complexity that they are, for all meaningful purposes, simply more points of matter in the void. And the solar system itself, even with its planets, its asteroid belts, its comets and dust, and the faint thin shell of debris at its outer edges, is still almost entirely empty space. The total volume occupied by the sun, all 8 planets, all their moons, all the asteroids and comets and dust. If you gathered every particle of solid and liquid matter in our entire solar system and pressed it together, you would have an object that is an almost infinitely tiny fraction of the total volume the solar system occupies. The solar system is not a collection of objects floating in space. It is space, with a few extraordinary exceptions drifting through it. Let me give you one more number to anchor this feeling before we move further out. The distance from the Earth to the Sun, 150 million kilometers, a distance we call 1 astronomical unit, or simply 1 AU, is a span that light crosses in about 8 minutes. 8 minutes of travel at the maximum speed the universe permits. The distance to Pluto, at the far edge of our solar system's classical structure, is roughly 40 AU. Light takes about 5.5 hours to travel from the Sun to Pluto. 5.5 hours for the fastest thing in the universe to reach what we still loosely call a member of our solar family. In between, there is nothing. Enormous, patient, indifferent nothing, through which the planets drift like dust motes in a cathedral the size of a continent, and through which the Voyager spacecraft, the furthest human-made objects ever launched, have been travelling for nearly 50 years and still have not truly left. This is the scale problem, and it does not get easier as we go outward. In fact, the further we travel from this grapefruit sun, the more completely the emptiness takes over. Our solar system sits inside the Milky Way galaxy, which is itself a structure of staggering size, and the Milky Way sits inside a local group of galaxies, which sits inside a supercluster, which sits inside a cosmic web of structure that spans hundreds of millions of light years. At every level of this zoom, the pattern repeats. Matter exists. Matter is real and present and in places extraordinarily dense, but matter is always, always the exception. The void is always, always the rule. And as we continue our journey tonight, as we push further out from our familiar sun and our familiar sky, the rule is going to become harder and harder to look away from. I want to take you on a journey tonight. Not a fast one. Not the kind of journey that science fiction has trained us to expect, with stars blurring into streaks and destinations arriving in seconds. I want to take you on the real journey, the slow one, the one that reveals, with every passing hour and every passing day, just how much of space is not space at all, just how much of it is simply, completely, nothing. We're going to leave Earth together and travel outward through our solar system, stopping at each world in turn, and I want you to pay attention not to the planets themselves, but to what lies between them, because that is where the truth of the solar system lives, not in its rocks and gases and storms, in its silences. We begin, as all journeys from Earth must, by leaving the only home our species has ever known. From the surface of the Earth to the edge of our atmosphere, the thin blue shell of air that makes all life possible is roughly 100 kilometers. 100 kilometers. That sounds like a reasonable distance. You could drive it in an hour on a clear road. But cross that invisible line and everything changes. The air thins to nothing. The sky, which from the ground appears as a deep and reassuring blue, turns black. Not the black of night, where your eyes can still find shapes and shadows, but a black so absolute and so final that it feels less like a colour and more like an absence. You are in space now. And space, from the very first moment, announces its nature clearly. It is empty, it is cold, and it does not care. From the edge of our atmosphere, the moon hangs at a distance of roughly 384,000 kilometers. That is the closest significant object to us in space, our companion, our nearest neighbour, the only other world a human being has ever stood on. And even at that relatively modest distance, the journey reveals something important. If you were to travel from the Earth to the moon by car, driving at highway speed without stopping, it would take you roughly 5 months. 5 months of driving through nothing, through a vacuum so complete that a single unprotected breath would be your last, through a cold so absolute it makes the coldest place on Earth feel like a warm afternoon. And the moon is close. In solar system terms, the moon is practically touching us. Now let us continue outward toward the sun. Between the Earth and the sun lies 150 million kilometers of interplanetary space. This region is not quite empty in the strictest technical sense. It contains the solar wind, a constant stream of charged particles flowing outward from the sun, and occasional wisps of dust and gas too thin and too sparse to see or feel. But it is, for any practical purpose, a void. There are no landmarks. There is no sensation of movement without a reference point. There is nothing to tell you that you are travelling at all except the slow, almost imperceptible growth of the sun ahead of you, and the equally slow shrinking of the blue dot behind. When the Mariner and Pioneer probes crossed this distance in the early decades of space exploration, their transmissions came back describing not wonder and abundance, but an almost oppressive, unbroken sameness. Empty space in every direction, for as far as instruments could measure. Beyond the Earth, continuing outward, we pass Mars at roughly 228 million kilometers from the Sun, depending on where both planets sit in their orbits. Then comes the asteroid belt, a region that, in popular imagination, is often depicted as a dense and dangerous obstacle course of tumbling rocks. The reality is almost comically different. The asteroid belt is so vast and its constituent rocks so spread out that if you were to travel through it, you would almost certainly never see a single asteroid with the naked eye. The average distance between asteroids in the belt is roughly 960,000 kilometers. You could drive for nearly 1 million kilometers in any direction and encounter nothing but emptiness. The asteroid belt is not a wall of rock. It is a suggestion of rock, scattered across a volume of space so large that the rocks themselves are irrelevant to the emptiness around them. Jupiter waits at roughly 778 million kilometers from the Sun. To put that in terms of travel time, light, moving at 186,000 miles per second, takes roughly 43 minutes to cover that distance. A spacecraft travelling at the speed of the fastest probes ever launched would take years. Years of crossing a space so uniformly empty that mission controllers on Earth must plan every manoeuvre months in advance, because there is simply nothing out there to adjust course against, nothing to shelter behind, nothing that distinguishes one patch of void from another, except the slow drift of the stars in the background. Jupiter itself is a planet of staggering size, large enough to swallow 1,300 Earths, and yet it occupies only the most infinitesimal fraction of the volume of space it moves through. And then there is Voyager 1. Launched in the autumn of 1977, Voyager 1 is the furthest human-made object ever sent into space. As of the time I am speaking to you, it sits at a distance of more than 23 billion kilometers from the Sun, well beyond the orbit of Neptune, beyond the Kuiper Belt, out in a region called the heliosphere's outer edges, where the Sun's influence finally begins to give way to the true interstellar medium. Voyager 1 has been travelling for nearly 50 years. It moves at roughly 61,000 kilometers per hour. And in all that time, crossing all those billions of kilometers, it has encountered almost nothing. A few instruments registering the thinning of the solar wind, a gradual increase in the density of cosmic rays from outside the solar system. No rocks, no dust clouds worth mentioning, no obstacles, just space, and the patient hum of instruments that were built by human hands are powered by the slow decay of plutonium and are still, impossibly, sending signals back across the void. There is something deeply moving about Voyager 1, and I want to sit with it for a moment before we move further outward. It is a machine, a collection of metal and wire and silicon assembled in a laboratory in California almost 5 decades ago. It weighs roughly 825 kilograms, about as much as a small car, and it is right now drifting through a silence so complete and so ancient that the nearest star beyond our Sun is still more than 4 light-years away from where it floats. It carries a golden record, a disk encoded with sounds and images and greetings from Earth, a message in a bottle thrown into an ocean that has no shore. When we think about the emptiness of the solar system, I find it helps to think about Voyager, not as a triumph of engineering, though it is that, but as a measure of the void, a tiny, warm, human-made thing drifting alone through a darkness that will not end for thousands of years, even at its current speed. The solar system is mostly nothing, and Voyager 1 is our most honest witness to that fact. When Voyager 1 finally crossed the boundary of the heliosphere, that invisible frontier where the sun's outward breath of charged particles finally loses the battle against the pressure of the wider galaxy, scientists gave that moment a name. They called it the heliopause. And on the other side of the heliopause, Voyager 1 entered a place that has no comfortable human name, because no human language developed in a world where such a place needed one. It entered interstellar space. True interstellar space. The space between the stars. And what it found there, what its instruments began to register as it crossed that threshold in the year 2012, was something that even scientists who had spent decades preparing for that moment described with a kind of reverent unease. It was not different from the space inside our solar system in any dramatic, visible way. It was simply more empty, more cold, more ancient, more final. Interstellar space is not the same as the vacuum between planets. Both are, to human senses, indistinguishable from absolute nothing. But interstellar space has properties that make it a different category of emptiness entirely. Inside our heliosphere, the sun's constant outpouring of particles, the solar wind, maintains a kind of thin, warm, dynamic environment. It is still a near-perfect vacuum by any laboratory standard, but it is a vacuum with character, with movement, with the sun's fingerprint pressed into every cubic meter of it. Cross the heliopause and that fingerprint disappears. The solar wind stops. The temperature of the particles, such as they are, drops further. The density of matter, already almost inconceivably low inside our solar system, drops further still. You are now in a medium so thin, so cold, and so uniform that the very concept of temperature becomes difficult to apply in any intuitive sense. Here is a number that has stayed with me since I first encountered it, and I want to share it with you now because I think it does more honest work than almost any other figure in astronomy. In the best vacuum chambers that human engineers have ever built on Earth, rooms evacuated of air to the lowest pressures our technology can achieve, there are still roughly 10 million molecules per cubic centimetre. 10 million. In the interstellar medium, the average density of matter is approximately 1 atom per cubic centimetre, not 10 million. 1. A single hydrogen atom, floating alone in a volume the size of a sugar cube, with its nearest atomic neighbour perhaps another cubic centimetre away. The best vacuum we have ever engineered on the surface of this planet is, by the standards of interstellar space, a thick and crowded soup. The void between the stars makes our finest laboratory achievements look almost embarrassingly dense. And the cold. I want to talk about the cold, because it is a different kind of cold from anything you have ever experienced or ever could experience on Earth. The temperature of the interstellar medium varies depending on where you are within it. There are warm regions near energetic stars and cool regions far from any significant heat source. But in the coldest, most isolated stretches of interstellar space, temperatures approach just a few degrees above absolute zero. Absolute zero is the point at which matter contains, theoretically, no thermal energy whatsoever, no vibration, no movement at the atomic level, zero. The coldest naturally occurring environments we have found in the universe hover at around 1 degree above that absolute floor. 1 degree. The difference between absolute zero and the coldest parts of interstellar space is roughly the difference between complete atomic stillness and the faintest, most imperceptible tremor. It is a cold that does not merely chill. It is a cold that simply is. It has been that cold in those places for billions of years, and it will remain that cold for billions more. Now consider what it means to cross this desert between stars. The nearest star system to our own, Alpha Centauri, a triple system containing 2 sun-like stars and the red dwarf Proxima Centauri, lies 4.2 light-years away. We established this earlier in our journey, but I want to return to it now with fresh weight, because now you understand something about what fills that 4.2 light-years. Nothing fills it. Or rather, 1 hydrogen atom per cubic centimetre fills it, which is as close to nothing as physics currently permits matter to be, while still technically existing. Across that entire distance, 25 trillion miles, a span that light takes 4.2 years to cross, there is no warmth, no density, no shelter, no reference point, no landmark, no sound, no colour, no sensation of any kind that a human nervous system could register. Just the faint ancient hum of cosmic background radiation left over from the Big Bang, pervading every cubic centimetre of the universe equally, a whisper from 13.8 billion years ago that never quite goes away. There is a thought experiment I find both beautiful and deeply unsettling, and I want to offer it to you now as we drift through this interstellar desert together. Imagine a civilization, somewhere, somewhen, that managed to build a spacecraft capable of travelling at 1% of the speed of light. 1%. That is roughly 3,000 kilometers per second, a speed so far beyond anything human engineering has achieved that it belongs entirely to the realm of speculation and hope. At 1% of light speed, a journey to Proxima Centauri would take approximately 420 years. 420 years of crossing the interstellar medium. Every day of that journey would look identical to every other day. Every instrument reading would be essentially unchanged. 1 atom per cubic centimetre in every direction. A temperature just barely above absolute zero. The sun behind you shrinking imperceptibly. The triple star system of Alpha Centauri ahead growing imperceptibly. And between those 2 points of light, nothing. Just nothing. For 4 centuries. And yet, and this is what keeps this from being simply a meditation on despair, that nothing is not passive. It is not inert. The interstellar medium, as empty as it is also a medium through which things travel. Light travels through it, crossing the galaxy over tens of thousands of years, carrying information about the stars that emitted it. Cosmic rays travel through it, high-energy particles accelerated to near light speed by supernovae and black holes, crossing the galaxy in all directions, threading through the void without obstruction. Gravity travels through it, silently and instantaneously by the standards of our experience, binding stars into galaxies and galaxies into clusters across distances that dwarf even the interstellar gaps we have been describing. The interstellar desert is empty of matter, but it is not empty of influence. It is a vast, quiet medium through which the universe communicates with itself across distances that stagger the imagination. And we, here on our small warm planet surrounded by our thin and precious atmosphere, are the beneficiaries of everything that has travelled through that void to reach us. Every photon of starlight that has ever touched your eye made that crossing. Every piece of information we have ever gathered about the cosmos arrived here through the interstellar desert, carried by nothing more than a ripple in a field, crossing an emptiness so profound it has no equal anywhere in human experience. We have travelled far tonight. We left the surface of the Earth, crossed the solar system with its thin scattering of planets and its vast corridors of interplanetary emptiness, and then pushed further still into the interstellar desert, that place between stars where a single hydrogen atom per cubic centimetre is all that stands between the void and absolute nothing. And at each step, the emptiness has grown. At each step, the universe has revealed a little more of its true character. But I need to tell you now that everything we have described so far, the gulf between planets, the desert between stars, is, by the standards of the largest structures in the universe, practically cozy, practically intimate, because we have not yet left our galaxy. We have not yet looked at what lies between the galaxies themselves, and when we do, the scale of emptiness we encounter is so extreme that even the words we have been using will start to feel inadequate. The Milky Way, our home galaxy, is a barred spiral, a rotating disk of stars, gas, dust, and dark matter, roughly 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars, and it has been forming those stars, burning and exploding and recycling matter through stellar generations for nearly as long as the universe itself has existed. It is, by any human measure, an object of incomprehensible size and richness. And yet the Milky Way is not alone. It belongs to a small gathering of galaxies called the Local Group, which contains roughly 50 galaxies in total, the largest of which are our own Milky Way and the Andromeda Galaxy, sitting about 2.5 million light-years away. 2.5 million light-years of intergalactic space separating two of the largest members of our cosmic neighbourhood, and in that 2.5 million light-year gap the density of matter drops below even the extraordinary thinness of the interstellar medium. In the space between galaxies, there is less than 1 atom per cubic metre, not per cubic centimetre, per cubic meter, a volume the size of a large refrigerator containing a single particle of matter drifting in a cold and featureless dark that has existed since before the Earth was born. But here is what I find genuinely astonishing, and a little terrifying when I think about the large-scale structure of the universe. The local group, with all its 50 galaxies, is itself a small and rather unremarkable feature in a far larger architecture. Astronomers looking at the distribution of galaxies across the observable universe have found something that stops every conversation when you first encounter it. The universe is not randomly scattered with galaxies. It has structure. Enormous, intricate, almost organic-looking structure. Galaxies cluster together along vast filaments, thread-like strands of matter stretching hundreds of millions of light-years. And these filaments connect at nodes where particularly dense clusters of galaxies gather. Between the filaments, between the nodes, between all the places where matter has managed to collect, there are voids. Enormous, spherical, almost perfectly empty regions of space, with no galaxies, no significant gas, no stars, just nothing. And these voids are not small. The Bootes void is one of the largest known voids in the observable universe, and it is worth spending a moment with because its scale defies easy absorption. Discovered in 1981 by astronomer Robert Kirshner and his colleagues, the Bootes void is a roughly spherical region of space, approximately 330 million light-years across. Inside a volume that large, you would expect, based on the average distribution of galaxies in the universe, to find thousands of galaxies. When astronomers looked into the Bootes void, they found approximately 60 galaxies in a space large enough to contain thousands. The rest is simply absent. If our Milky Way were located somewhere inside the Bootes void, rather than in our actual corner of the universe, our astronomers for most of human history would have had no idea that other galaxies even existed. The nearest galactic neighbour would have been so far away that it might have been beyond the reach of the telescopes we built in the 20th century. We would have looked out from our world and seen, in most directions, only empty darkness. The cosmic web, that structure of filaments and voids that describes the large-scale architecture of the universe, is one of the most striking images that modern cosmology has produced. When astronomers map the positions of millions of galaxies and render that map in 3 dimensions, what emerges looks startlingly like a biological structure. It resembles the neural network of the human brain, or the interior of a sea sponge, or the structure of certain fungi, long branching connections surrounding hollow spherical spaces. The resemblance is not coincidence in the deepest sense, because the same physics that governs the formation of large-scale cosmic structure, gravity pulling matter together along lines of slight density variation in the early universe, also governs the growth of branching biological structures. The universe at its largest scale looks like something alive, and yet those vast bubbles surrounded by glowing filaments are not filled with life or warmth or activity. They are filled with almost nothing. The cosmic web is the architecture of emptiness, decorated at its edges by the rare and precious accident of matter. I want to give you a sense of the intergalactic medium, the thin gas that fills the space between galaxies even in the relatively populated regions of the cosmic web. Unlike the interstellar medium inside galaxies, the intergalactic medium is not primarily hydrogen in its neutral form. It is a plasma, hydrogen and helium that have been ionized, stripped of their electrons, by the intense radiation of the first stars and quasars that lit up the early universe. This plasma is extraordinarily hot. Temperatures of 100,000 to 10 million degrees are common, but also extraordinarily thin. Hot and thin in physics are not contradictory. Temperature measures the energy of individual particles, not their density. The intergalactic plasma is hot because its particles move fast, but those particles are separated by distances so vast that the total energy in any given volume is almost nothing. If you were somehow immersed in the intergalactic medium, you would not feel warmth. You would feel the killing cold of near absolute vacuum, because so few of those energetic particles would actually strike you that your body's heat loss would vastly outpace any energy absorbed. And so we arrive at a picture of the universe that is both magnificent and, once absorbed, profoundly humbling. A cosmic web of filaments and nodes traced in the light of billions of galaxies, surrounding voids so vast that entire civilizations could live and die inside them without ever suspecting that the rest of the universe existed. Between the galaxies, a plasma so thin and so removed from any ordinary experience of matter that our language of density and temperature barely applies. And at the nodes and filaments, those precious thin threads where matter has gathered, galaxies like ours, burning their stars over billions of years, generating light that crosses the intergalactic abyss for millions or billions of years before encountering another significant structure. We are not living in a full universe. We are living on a thread of a web, suspended over voids that make our solar system's emptiness look like a crowded city street. The abyss is not somewhere else. It is everywhere. We are the rare exception, floating in an ocean of absence that stretches in every direction further than the mind can honestly follow. I want to stop our journey outward for a moment. We have been travelling, you and I, through increasingly vast scales of emptiness, from the gaps between planets, to the deserts between stars, to the abyssal voids between galaxies. And at every scale, the story has been the same. Matter is rare. Space is dominant. The universe, by volume, is almost entirely empty. But here is the thing most people do not realise, and it is the kind of thing that, once you hear it clearly and let it settle, changes the texture of everything that came before. All of that emptiness we have been describing, all those trillions of light years of void, is not even the strangest part of the inventory. Because when scientists sat down and tried to account for everything the universe contains, they discovered something so shocking, so quietly destabilizing, that it rewrote the foundations of cosmology almost overnight. It turns out that the matter we have been talking about, the stars, the planets, the gas, the dust, the atoms of hydrogen drifting alone through the interstellar medium, all of it, everything we can see and touch and measure, makes up only about 5% of the total content of the universe. 5%. The other 95% is something else entirely. Let me say that again, because it deserves to be heard slowly. Every star you have ever seen, every planet in every solar system, every galaxy in the cosmic web, every atom of hydrogen in the interstellar desert, every wisp of intergalactic plasma, every grain of dust orbiting a distant sun, all of it, the totality of everything that has ever been observed, measured, photographed, or theorized about in the history of human science, adds up to roughly 5% of what the universe actually contains. The remaining 95% is divided between two things we cannot see, cannot touch, cannot directly detect, and do not, in any honest sense, understand. We have given them names, dark matter and dark energy, because naming things is what humans do when we encounter what we cannot explain. But the names are placeholders. They are labels on doors we have not yet opened. Dark matter accounts for approximately 27% of the universe's total content. Dark energy accounts for approximately 68%. Together they make up the overwhelming majority of everything that exists, and both of them are invisible. Both of them interact with the world we know in ways that are indirect, subtle, detectable only through their effects on the matter and light we can observe. We have never captured a particle of dark matter in a laboratory. We have never isolated a unit of dark energy for study. We infer their existence the way a detective infers the presence of someone who has left the room, from the furniture that has been moved, from the footprints in the dust, from the things that should be there but are not quite right without an invisible hand to explain them. The universe's inventory, when honestly taken, is 95% mystery, and we have been spending our entire scientific history studying the remaining 5%, sometimes forgetting to mention that the shelves behind us are almost entirely full of things we cannot name. The story of how we discovered this begins in the middle of the 20th century, in observatories where astronomers were doing something deceptively simple. They were measuring how fast galaxies rotate. When you spin a solid disk, a vinyl record for instance, every part of it rotates at the same rate. The outer edge and the inner edge complete one revolution in the same time, but galaxies are not solid disks. They are collections of stars held together by gravity, and gravity weakens with distance, so you would expect the outer stars of a galaxy to orbit more slowly than the inner stars, just as the outer planets of our solar system orbit more slowly than the inner ones. Pluto moves far more slowly around the Sun than Mercury does. This is basic, well-understood orbital mechanics, confirmed everywhere we have ever looked. And so, when astronomer Vera Rubin and her colleague Kent Ford measured the rotation of the Andromeda Galaxy in detail in the 1960s and 70s, they expected to find the outer stars moving slowly. They did not. The outer stars were moving at roughly the same speed as the inner stars. The rotation curve was flat when it should have been declining. Something was wrong, or rather, something was missing. The only explanation that fit the data, and it has now been confirmed in hundreds of galaxies, through multiple independent methods, over half a century of increasingly precise measurement, is that there is more mass in galaxies than we can see. A great deal more. Something invisible, distributed in a vast halo around the visible matter of each galaxy, providing the gravitational glue needed to explain the rotation curves. Something that does not emit light, does not absorb light, does not interact with electromagnetic radiation in any way we have yet detected. Matter that is there, emphatically and measurably there, and yet completely dark to every instrument we point at the sky. Vera Rubin's observations were not immediately celebrated. They were questioned, doubted, and in some quarters dismissed. But the data did not change. The flat rotation curves remained flat, and eventually the scientific community arrived at a conclusion it is still not entirely comfortable with. Most of the matter in the universe is invisible. Most of the architecture of the cosmos is made of something we cannot see. And then there is dark energy, which is stranger still, and which we will explore in more depth in the next part of our journey. For now, I want you to hold the number, 68%. More than 2/3 of the entire content of the universe is a form of energy so diffuse, so uniformly distributed through space, so unlike anything in our ordinary experience that we detect it only by its effect on the largest structures in the cosmos. We see galaxies moving apart from each other faster than gravity alone can explain, and we infer from that acceleration the presence of something pushing outward, something embedded in the fabric of space itself, something that grows stronger as space expands because it is not diluted by expansion the way matter is. We call it dark energy. We know it is there. We do not know what it is. So here tonight is the honest inventory of the universe. 5% ordinary matter, the stuff of stars and planets and people and everything that has ever been built or named or loved. 27% dark matter, invisible, structurally essential, gravitationally real, and fundamentally mysterious. 68% dark energy, the dominant force shaping the fate of the cosmos, accelerating the expansion of space, and utterly beyond our current physical understanding. We live in a universe where almost everything is empty, and almost everything that fills that emptiness is something we cannot see. The visible universe, the stars, the galaxies, the cosmic web we mapped with such pride, is a faint tracing on the surface of something vast and dark and unknown. It is, when you let the numbers land properly, one of the most humbling facts in all of human knowledge. We are not studying the universe, we are studying its shadow. Imagine you are walking through a city at night. Not a city with streetlights and neon signs, but a city completely dark, every building unlit, every window black, every street lamp cold and dead. And yet, as you walk, you notice something. The traffic is flowing. Cars are stopping at intersections, turning corners, navigating the streets with perfect precision, as if the roads and buildings and traffic signals are all exactly where they should be. You cannot see the infrastructure. You cannot see the roads or the curbs or the bridges, but you can see the traffic, and the traffic tells you, unmistakably, that an infrastructure is there. Something is shaping the movement of everything around you, even though that something is entirely invisible. This, as closely as any everyday analogy can capture it, is what dark matter is. We cannot see it. We cannot touch it. We have never held a particle of it in a laboratory, but we can see the traffic, the motion of stars, the bending of light, the large-scale architecture of the cosmic web, and the traffic tells us, with a precision that has now been confirmed through decades and multiple independent lines of evidence, that something invisible is shaping everything. The evidence for dark matter does not rest on a single observation. That is what makes it so difficult to dismiss and so important to genuinely absorb. It comes from at least 4 completely different directions, each of them pointing to the same conclusion. The first, as we touched on last chapter, is galactic rotation. Stars in the outer regions of galaxies orbit too fast to be explained by the gravity of the visible matter alone. The second line of evidence comes from gravitational lensing, the bending of light from distant objects as it passes through regions of strong gravity. When astronomers map the way light bends around galaxy clusters, they find that the total gravitational mass of those clusters, as revealed by the lensing, is far greater than the mass of the visible stars and gas. Something unseen is bending the light. Something massive and dark is sitting between us and the distant sources, warping the fabric of space-time in ways that require more mass than we can account for with anything we can observe. The third line of evidence comes from the large-scale structure of the universe itself, the cosmic web we described in the previous chapter. The filaments and voids, the clusters and superclusters, did not form randomly. They grew from tiny fluctuations in the density of the early universe, slight variations in how matter was distributed in the first moments after the Big Bang, amplified over billions of years by gravity. But when cosmologists run the calculations using only ordinary matter, the structures they get do not match what we observe. The cosmic web as it actually exists, with its enormous filaments and vast voids, only emerges in the simulations when dark matter is included. Without the invisible scaffolding, the galaxies do not cluster correctly. The web does not form. Our universe, as we observe it, is only possible if most of its matter is something we cannot see. And the fourth line of evidence is perhaps the most visually striking of all. In 2006, astronomers studying a colossal collision between two galaxy clusters, an event called the Bullet Cluster, were able to do something remarkable. They mapped both the ordinary matter and the gravitational mass of the merging system separately. The ordinary matter, the hot gas that makes up most of the visible mass in galaxy clusters, was slowed and distorted by the collision, forming a distinctive bullet-shaped shockwave in between the two clusters. But the gravitational mass, as mapped by lensing, did not follow the gas. It passed through the collision mostly unaffected, continuing in the original direction of each cluster, as if the collision had barely happened. The dark matter and the ordinary matter had separated. The dark matter, not interacting electromagnetically, had simply passed through the collision, like two swarms of ghosts walking through each other, while the gas, which does interact electromagnetically, was slowed and compressed into the bullet shape. It was, in effect, the closest thing to a direct photograph of dark matter's behaviour that science has ever produced. Not a photograph of dark matter itself, but a photograph of its absence from a collision that should have deflected it if it were anything like ordinary matter. So what is dark matter? Here is where honesty requires a moment of humility. We do not know. We have a long list of candidates, hypothetical particles that would have the right properties to explain the observations, and we have been searching for them for decades, in underground laboratories shielded from cosmic ray interference, in data from the Large Hadron Collider, in signals from space-based instruments. The leading candidate for many years was a class of particles called WIMPs, weakly interacting massive particles, which would interact with ordinary matter only through gravity and the weak nuclear force, making them almost impossible to detect directly. But decades of increasingly sensitive searches have not found WIMPs. Each new generation of experiments has set tighter limits on where WIMPs could be hiding, and each generation has come up empty. Other candidates include axions, sterile neutrinos, and more exotic theoretical constructs. Some physicists have proposed modifications to gravity itself as an alternative explanation. None of these alternatives has yet been confirmed. Dark matter remains, after nearly a century of increasingly sophisticated investigation, a mystery that the best minds in physics have not been able to crack. What we can say with confidence is what dark matter does, even if we cannot say what it is. It forms enormous halos around galaxies, invisible spherical clouds of mass extending far beyond the visible disk of stars, providing the gravitational environment that allows galaxies to hold together and rotate as they do. Without these halos, galaxies as we know them would not exist. The stars in the outer regions of the Milky Way would drift outward and disperse, unable to maintain their orbits against the meagre gravity of the visible mass alone. Dark matter is not a peripheral feature of the universe. It is structural. It is the invisible skeleton on which the visible universe has been built, the armature beneath the sculpture, the frame inside the wall. Every galaxy you have ever seen in a photograph, every spiral, every elliptical, every irregular smear of light across the deep field images, is embedded in a halo of dark matter many times more massive than the stars it contains. There is something I find genuinely moving about this, beneath the unease. We built our understanding of the universe on what we could see, on the light that crossed billions of light years to reach our instruments, on the photons that carry the stories of distant stars and ancient explosions. And then, carefully, honestly, following the evidence wherever it led, we discovered that what we could see was only a small fraction of what was actually there. We discovered that the universe had been shaped from the very beginning by something we had no instruments to detect and no theory to fully describe. The invisible architecture was always there. The dark scaffolding was always holding everything up. We just had not yet learned to read the traffic patterns that revealed it. That kind of discovery, humbling, disorienting, and ultimately expansive, is what science, at its best, actually feels like. Not the comfortable confirmation of what we already believed, but the quiet vertigo of realizing that the map was always smaller than the territory. In the year 1998, 2 independent teams of astronomers set out to measure something they thought they already understood. They were studying a specific type of exploding star, a Type 1 a supernova, that burns with such a consistent and predictable brightness that astronomers use them as cosmic rulers. Because you know exactly how bright the explosion truly is, you can calculate precisely how far away it must be based on how dim it appears from Earth. The teams were using these stellar rulers to measure the rate at which the universe was expanding, fully expecting to find what most physicists at the time assumed, that the expansion was slowing down. Gravity, after all, pulls matter together. The Big Bang had flung everything outward, but gravity should have been acting as a brake, decelerating that expansion over the billions of years since the beginning. The question they were trying to answer was not whether the expansion was slowing, but by how much. What they found instead was one of the most shocking discoveries in the history of science. The expansion was not slowing down, it was speeding up. Let that sit for a moment. The universe is not just expanding. It has been expanding since the Big Bang, and that much was already known and accepted. What the supernova teams discovered in 1998 was that the rate of expansion is increasing. Galaxies are not just moving apart from each other, they're accelerating away from each other. The further a galaxy is from us, the faster it is receding, and that recession is getting faster over time, not slower. Gravity, the great assembler, the force that built every star and planet and galaxy in the cosmos, is losing. Something else. Something with no name in the physics of the time, something that had never been anticipated by any mainstream cosmological model, was pushing outward with a force strong enough to overwhelm the gravitational pull of all the matter in the universe. The discovery was so unexpected, so resistant to any existing theoretical framework, that the team sat on their data for months before publishing, checking and rechecking their results, looking for any possible error. There was no error. The universe was accelerating, and they had no idea why. The Nobel Prize in Physics for 2011 went to Saul Perlmutter, Brian Schmidt, and Adam Rees, the leaders of those 2 competing teams, for what their discovery revealed. We now call the cause of the accelerating expansion dark energy. It is the dominant component of the universe, making up approximately 68% of its total energy content. It is not a force in the way gravity or electromagnetism are forces, operating between particles or objects. It appears instead to be a property of space itself, an energy intrinsic to the vacuum, present everywhere, in every cubic centimetre of the universe, and unlike matter or radiation, it does not dilute as space expands. In fact, as space expands and creates more volume, the total amount of dark energy increases because more space means more of the energy embedded in space. This is what makes it so strange and so unlike anything in our ordinary experience. It does not fade with distance, it does not weaken over time. It is woven into the structure of reality at the most fundamental level, and as the universe grows, it grows with it. Here is a way to feel the strangeness of dark energy more concretely. Imagine you are blowing up a balloon. As the balloon expands, the air inside it spreads out. The density of air molecules decreases, the pressure drops. That is how ordinary matter and energy behave in an expanding universe. As space grows, the stuff inside it spreads thinner, but dark energy does not behave this way. It is more like a property of the rubber itself. As you stretch the balloon, you do not dilute the property. You create more of it because you have more rubber. The expansion of the universe does not diminish dark energy. It feeds it. And as dark energy grows with the growing universe, its influence over that universe grows correspondingly. This is why the expansion is accelerating. This is why the universe, left to its own dynamics, is not coasting toward some equilibrium, but racing, with increasing urgency, toward an outcome that is almost incomprehensible in its finality. The theoretical framework most physicists currently use to describe dark energy is something called the cosmological constant, a term that Albert Einstein introduced into his equations of general relativity in 1917 and then famously removed, calling it his greatest blunder, when Edwin Hubble's observations confirmed that the universe was expanding rather than static. Einstein had introduced the constant as a kind of repulsive term to balance gravity and maintain a static universe, because a static universe was what he, and essentially everyone else at the time, assumed existed. When expansion was confirmed, the balancing act seemed unnecessary, and Einstein withdrew the term. But the supernova observations of 1998 suggested that something very much like Einstein's cosmological constant was not just present, but dominant. His greatest blunder may have been removing it. The universe, it seems, contains exactly the kind of repulsive energy he had invented and then discarded. What does dark energy mean for the future of the universe? The implications are, depending on your temperament, either deeply sobering or strangely beautiful. As dark energy continues to accelerate the expansion of space, the distance between galaxy clusters will grow. Galaxies that are not gravitationally bound to our local group are already receding from us, and as the expansion accelerates, they will recede faster and faster. Eventually, in tens of billions of years, the most distant galaxies will be receding from us faster than the speed of light. Not because they are moving through space faster than light, which relativity forbids, but because the space between us and them will be expanding so rapidly that light emitted from those galaxies will never be able to cross the growing gap to reach us. They will pass beyond what cosmologists call the cosmic event horizon. They will become permanently, irreversibly unreachable and invisible. Any civilization alive in the universe at that distant time, looking out at the sky, would see far fewer galaxies than we can see today. The universe will appear smaller, emptier, more alone. And this process, given enough time, does not stop at the level of galaxy clusters. Models of an accelerating universe suggest that eventually the expansion will become strong enough to overcome the gravity binding individual galaxies together, then the gravity-binding star systems, then the electromagnetic forces holding planets and rocks, and eventually atoms together. In the most extreme versions of this scenario, called the Big Rip, dark energy ultimately tears apart every structure in the universe, from galaxy clusters down to protons and neutrons, ending in a state of total, perfectly smooth, infinitely expanded nothing. Most cosmologists consider the Big Rip unlikely given current measurements of the rate of acceleration, but the direction of travel is not in doubt. The universe is expanding, the expansion is accelerating, the emptiness is growing, and the force responsible for that growth is winning, has always been winning, and shows no sign of slowing. Whatever dark energy is, it is patient. It has been quietly at work since before the first stars lit the first galaxies, and it will be at work long after the last star has burned to cold silence. We have been travelling, you and I, through an increasingly sobering portrait of the universe. We have measured its emptiness at every scale. We have discovered that most of its matter is invisible, and that most of its content is a mysterious energy pushing everything apart. We have seen that the visible universe, all the stars and galaxies and beautiful structures we have spent centuries mapping and naming and marvelling at, amounts to just 5% of what actually exists. And yet here we are. You are here. I am here. This planet is here. Warm and improbable, covered in oceans and forests and cities and music and grief and love and all the staggering complexity that life generates when given a few billion years in the right conditions. And tonight I want to turn the question around. Not why is the universe so empty, but why does it contain anything at all? Because it almost did not. The universe came extraordinarily, terrifyingly close to containing nothing but light. And the reason it does not, the reason matter exists, is one of the strangest and most beautiful accidents in the history of everything. To understand why matter exists, we need to go back to the very beginning. Not the beginning of the solar system, not the beginning of the Milky Way, but the beginning of the universe itself. In the first fractions of a second after the Big Bang, in intervals of time so small that they have no meaningful everyday analogy, the universe was unimaginably hot and dense. Not the mere millions of degrees of stellar interiors, but temperatures of trillions upon trillions of degrees, a state of energy so extreme that matter and energy were essentially interchangeable. And in this primordial furnace, the laws of physics that governed what existed mandated a perfect symmetry. For every particle of matter created in the chaos of the early universe, a corresponding particle of antimatter should have been created alongside it. Matter and antimatter, born in equal measure, mirror images of each other, opposite in charge and certain quantum properties, but identical in mass. Equal and opposite. Perfectly balanced. Here is what should have happened next if the universe had been perfectly fair. As the universe expanded and cooled from that initial extreme, every particle of matter should have encountered its antimatter partner. And when matter meets antimatter, they annihilate each other completely, converting entirely into energy, into photons of light. If matter and antimatter had been produced in exactly equal quantities, every particle of matter in the early universe would have found its partner, and every pair would have annihilated, and the universe would have been left with nothing but light. A vast, expanding ocean of photons, perfectly smooth, perfectly empty of structure, perfectly dead. No atoms, no chemistry, no stars, no planets, no history, no questions, and no one to ask them. The universe, if it had followed the most straightforward interpretation of its own laws, should have erased itself in its first seconds and left behind only a cooling glow of radiation, expanding forever into infinite featureless nothing. But that is not what happened. For reasons that physicists are still working to fully understand, the symmetry between matter and antimatter in the early universe was not perfect. It was broken by a margin so small it seems almost accidental, almost irrelevant. For every 1 billion particles of antimatter produced in the Big Bang, there were 1 billion and 1 particles of matter. 1 extra particle of matter for every billion pairs, a fraction so small that you could be forgiven for dismissing it as a rounding error. And yet that fraction, that vanishingly thin asymmetry, that 1 in a billion imbalance, is the reason the universe contains anything at all. The billion matter-antimatter pairs annihilated as expected, flooding the early universe with light. And the 1 remaining particle of matter, left without a partner, survived. Every atom in your body, every atom in every star, every atom of hydrogen drifting alone through the interstellar medium, all of it descends from that surplus. All of matter, as we know it, is the rounding error. Physicists have a name for this asymmetry. They call it baryogenesis, and it is one of the great unsolved problems in modern physics. We know the asymmetry happened because we exist. We know its magnitude, roughly, because we can measure the ratio of photons to matter in the universe today and work backward. But we do not fully understand why the symmetry was broken. The standard model of particle physics, best current description of fundamental particles and forces, predicts a matter-antimatter asymmetry, but not enough to account for all the matter we observe. Something is missing from our understanding. Some mechanism, operating in the extreme conditions of the first fractions of a second, tipped the scales just enough to save the universe from self-erasure, and we have not yet identified it with certainty. The existence of everything is explained by a process we do not fully understand, which is, if you let it land, a remarkable place for science to be. But the asymmetry of matter and antimatter is only the first improbability in the chain that led to us. Even after matter survived its near erasure, the path from a hot soup of elementary particles to the complex structures of the universe was not guaranteed. In the first few minutes after the Big Bang, as the temperature dropped to merely billions of degrees, protons and neutrons began combining to form the nuclei of the lightest elements: hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, lasted only about 3 minutes. 3 minutes in which the nuclear furnace was hot enough for fusion, before the expanding universe cooled beyond the threshold needed for those reactions. In those 3 minutes, the ratio of hydrogen to helium was set, roughly 3 parts hydrogen to 1 part helium by mass, and that ratio has governed the chemistry of the universe ever since. Had the fundamental constants of physics been slightly different, had the strong nuclear force been a little stronger or a little weaker, had the expansion rate been slightly faster or slower, the result could have been a universe of pure helium, or one with no helium at all, And in either case, the stellar processes that forge heavier elements and ultimately make chemistry and life possible would not have worked the same way. And then there are the quantum fluctuations. In the first moments of the universe, the distribution of matter was not perfectly smooth. Tiny variations in density, fluctuations at the quantum level, amplified by a period of extraordinary rapid expansion called inflation, left the early universe with regions that were slightly denser than average and regions slightly less dense. These tiny ripples, imprinted in the first instance of time, became the seeds of everything that followed. Gravity amplified the denser regions, pulling in more matter, building the first clouds of gas that eventually collapsed into the first stars. Without those quantum fluctuations, matter would have distributed itself smoothly and uniformly through space, and gravity would have had no foothold, no slight density variation to work with. The universe would have remained a smooth, featureless gas, expanding forever, never clumping, never igniting, never building anything more complex than a hydrogen atom. The cosmic web, the galaxies, the stars, the planets, the chemistry, the biology, all of it traces back to the tiny, random quantum tremors in the first fraction of a second of existence. We are here because the universe was not quite smooth. We are here because of imperfections so small they had no business mattering, and yet they mattered absolutely. After everything we have covered tonight, the vast emptiness between planets, the desert between stars, the abyss between galaxies, the invisible scaffolding of dark matter, the relentless push of dark energy, the near miraculous survival of matter itself. I want to take a moment to talk about what makes the exceptions so extraordinary. Because the universe is almost entirely empty, yes. Because matter is a vanishingly rare accident, yes. Because the visible cosmos is just a thin trace on the surface of something vast and dark and unknown, yes. All of that is true. But where matter does gather, where gravity wins its local battles against the overwhelming preference of the universe for void, what it builds is astonishing. Stars are not just points of light on a dark background. They are the universe concentrating its rarest resource into something that burns and radiates and forges and explodes and seeds the darkness with the raw material of everything that follows. Stars are miracles of compression in a universe that almost never compresses anything. And tonight I want to look at them clearly, not just as beautiful objects, but as the statistical anomalies they truly are. A star begins in darkness. It begins as a cloud of gas, mostly hydrogen, the simplest and most abundant element in the universe, the direct legacy of those first 3 minutes of Big Bang nucleosynthesis. These clouds, called nebulae, drift through the interstellar medium for millions of years, cold and diffuse, barely distinguishable from the emptiness around them. Then something disturbs them. Perhaps the shockwave from a nearby supernova, perhaps a gravitational nudge from a passing star system, perhaps simply the slow accumulation of their own mass beyond a threshold of stability. And when that disturbance comes, gravity takes over. The cloud begins to contract. As it contracts, it heats. As it heats, the pressure at its center rises. For millions of years, this process continues, the collapsing gas growing hotter and denser at its core, the outer layers still cold and dark, the whole structure suspended between the inward pull of gravity and the outward pressure of the heat building within. And then, at a temperature of roughly 10 million degrees, something ignites. Hydrogen nuclei begin to fuse into helium, a star is born, a fire lights in the dark, and it will burn for millions or billions of years, depending on its mass, holding the void at bay through the sheer thermodynamic stubbornness of nuclear fusion. Our sun is a good star to begin with, because it is the one we know most intimately, and because it is, as I mentioned earlier, magnificently ordinary. It has a surface temperature of roughly 5,500 degrees Celsius and a core temperature of approximately 15 million degrees. It fuses roughly 600 million tons of hydrogen into helium every second. Every second. 600 million tons of matter converted into energy through the most fundamental process the universe allows, all of it poured outward as light and heat that crosses 150 million kilometers to warm the surface of a small blue planet where, among other things, creatures evolved who eventually learned to measure the temperature of the thing that warmed them. The Sun has been doing this for about 4.6 billion years and has roughly another 5 billion years of hydrogen fuel remaining. It is, by stellar standards, middle-aged, steady, reliable, the kind of star that makes planets possible and gives life the time it needs to become complicated. But the Sun, for all its impressive numbers, is nowhere near the extreme end of what stars can be. The universe, when it concentrates matter, does not always stop at something as modest as our Sun. Sometimes it builds things that defy the intuitions built by a lifetime of living on a human scale. Consider the hypergiant stars, the largest stellar objects known to exist. Stephenson 218, a red hypergiant located in the constellation Scutum, holds the current record for the largest known star by radius. Its diameter is estimated at roughly 2,000 times that of our Sun. 2,000 times. If you place Stephenson 218 at the centre of our solar system, in the position currently occupied by the Sun, its surface would extend beyond the orbit of Saturn. Saturn, with all its rings, with all its moons, with all its magnificent complexity, would be swallowed inside the atmosphere of this single star. Earth would be vaporized so deep inside the star's outer layers that it would be, from the star's perspective, essentially part of the core. And yet even Stephenson 218, even this object so vast it makes the solar system look like a small room, is a rare anomaly in a universe that, in most places, contains nothing at all. At the other end of the stellar spectrum there are objects of a different kind of extreme. When a massive star, one significantly heavier than our Sun, exhausts its nuclear fuel and can no longer support itself against gravity's inward pull, it collapses catastrophically in a fraction of a second, triggering one of the most violent events the universe produces, a supernova explosion. The outer layers of the star are blasted into space with energies that briefly outshine entire galaxies, and the core, crushed by the inward collapse, becomes something almost impossible to describe in ordinary terms. If the core mass falls within a certain range, it becomes a neutron star, an object roughly 20 kilometers across, smaller than a city but containing more mass than the Sun. The density of a neutron star is so extreme that a single teaspoon of its material would weigh roughly 4 billion tons on Earth. 4 billion tons in a teaspoon. The atoms that once made up the core of a star are crushed so completely that electrons and protons merge into neutrons, and the neutrons themselves are pressed together until they touch, separated by nothing but the quantum mechanical pressure that prevents matter from collapsing further. A neutron star is, in a very real sense, a star-sized atomic nucleus, and if the collapsing core is massive enough to overcome even that quantum resistance, it does not stop at a neutron star. It keeps collapsing, past every threshold physics offers as a stopping point, until it becomes a singularity, a black hole. A region of space where gravity is so extreme that not even light can escape, where the normal fabric of space-time closes in on itself, where our physical laws cease to apply in their familiar forms. Black holes are the ultimate expression of matter's capacity to concentrate, the logical endpoint of a process that begins with a diffuse cloud of gas and ends in a point of infinite density. They are the universe's most extreme act of compression, the furthest possible departure from the emptiness that dominates everything else, and they are in their own way also empty, not of mass, but of the kind of structured matter we are familiar with. Inside a black hole, the distinction between matter and space breaks down entirely. It becomes something else, something we do not have the physics to describe. What I want you to feel as we linger among the stars tonight is the improbability of all of it. Every star in the universe is a local victory of gravity over the void, a place where the universe's preference for emptiness was temporarily, precarious, overruled. The hydrogen that fuels our Sun drifted for hundreds of millions of years as a cold, diffuse cloud before gravity gathered it. The iron in your blood was forged in the core of a star that lived and died before our solar system existed, scattered into the void by a supernova, drifting through interstellar space for millions of years before ending up in this corner of the galaxy, incorporated into the cloud that became the Sun and its planets, eventually cycling through generations of life until it arrived in the hemoglobin of your red blood cells. You're not separate from the stars. You're made of what the stars made, and what the stars made, they made from almost nothing, against almost impossible odds, in a universe that tried at every scale to remain empty. There is a turn I want to make now in our journey. We have been travelling outward, from the solar system to the interstellar medium, from the galaxy to the cosmic web, from the visible universe to the dark mysteries that surround it. We have been following the emptiness as it grows, scale by scale, until it encompasses almost everything that exists. But tonight I want to reverse direction. I want to travel inward. Because the emptiness we have been describing out there, in the vast spaces between stars and galaxies, has a mirror image down here, inside the matter we think of as solid and real and present. The chair you're resting in, the bed you're lying on, the air in your lungs, the hand you might raise to touch your face in the dark. None of these things are what they appear to be. None of them are solid in any meaningful sense. All of them, at the level where physics actually operates, are almost entirely empty. The universe's preference for void does not stop at the cosmic scale. It goes all the way down. The atom is the basic unit of ordinary matter, the building block from which all the familiar stuff of the world is assembled. There are roughly 92 naturally occurring types of atoms, corresponding to the 92 naturally occurring elements, and the differences between them, between hydrogen and carbon, between oxygen and iron, between gold and lead, come down to differences in the number of protons in their nuclei and electrons in their outer shells. But what all atoms share, regardless of their element, is a structure that is almost incomprehensibly empty. Every atom consists of a nucleus, a dense compact core of protons and neutrons, surrounded by electrons that occupy a kind of probabilistic cloud at enormous distances from the nucleus relative to its size. The nucleus is where essentially all the mass of the atom lives, and the nucleus is tiny, extraordinarily, almost absurdly tiny, relative to the total size of the atom. Here is the analogy that has helped generations of physics students grasp this, and I want to offer it to you now because I think it is one of the most quietly destabilizing comparisons in all of science. Imagine a hydrogen atom, the simplest atom, consisting of a single proton in the nucleus and a single electron orbiting it. Now imagine scaling that atom up until its nucleus is the size of a marble, a small glass marble sitting in your hand. At that scale, the electron would not be orbiting a few inches away, or a few feet away, or even across the room. At that scale, the electron would be orbiting at a distance of roughly 1 kilometre from the marble. 1 kilometre, a marble in the centre of a stadium, and the electron somewhere at the outer boundary of the city. And between the marble and the electron, in that entire kilometre of scaled-up atomic space, there is nothing. Not air, not energy in any tangible form, just the quantum fields that govern the electron's behaviour and the electromagnetic force that binds it to the nucleus. The atom is not a tiny solid ball, it is a tiny solar system, and like the solar system, it is almost entirely empty. Now consider what this means for the world around you. Every object you have ever touched is made of atoms. Every surface that has ever felt solid beneath your fingers, wood, stone, glass, skin, is a collection of atoms, and each of those atoms is, by volume, overwhelmingly empty space. The reason solid objects feel solid is not that they are packed with matter. It is that the electromagnetic forces between atoms, the repulsion between the electron clouds of neighbouring atoms, resist compression. When you press your hand against a table, you're not feeling the table's matter. You're feeling the electromagnetic resistance of the electron clouds in the table's atoms pushing back against the electron clouds in your hand's atoms. You have never touched anything, not in the literal matter-to-matter sense. What we experience as physical contact is an electromagnetic interaction between electron clouds separated by distances that, at the atomic scale, are comparable to the distances between planets in a solar system. And it goes further still, because the nucleus itself, that marble we placed at the centre of our kilometre-wide atom, is not a solid object either. It is a collection of protons and neutrons are themselves composite particles, each one made of smaller entities called quarks. 3 quarks are bound inside each proton and each neutron by the strong nuclear force, the most powerful of the fundamental forces operating at extremely short ranges, and the quarks themselves occupy only a fraction of the volume of the proton. The rest, even inside the nucleus, even in the densest part of the atom, is quantum fields and the energy of interaction. Matter, at its most fundamental level currently accessible to physics, is not stuff. It is not tiny hard balls of solid material arranged in various combinations. It is patterns of energy in quantum fields, organised by forces giving rise to the properties we measure and the interactions we observe. The solidity of the world is not a property of matter. It is a property of the forces between fields. The universe, from the largest voids between galaxy clusters down to the interior of a proton, is empty in ways our senses were never designed to perceive. I want to sit with the human dimension of this for a moment, because I think it deserves more than just a scientific acknowledgement. You are, right now, a collection of approximately 7 billion atoms. That is a 7 followed by 27 zeros. 7 billion atoms, arranged in a configuration of such staggering complexity that it can perceive, feel, remember, grieve, wonder, and lie awake at night thinking about the emptiness of space. And each of those atoms is, by volume, more than 99.999% empty space. If you could somehow compress all the actual matter in your body, all the nuclei of all your atoms, stripped of their electron clouds and pressed together until they touched, the result would be a sphere roughly the size of a grain of fine sand. A single grain of sand. That is how much actual matter a human body contains. The rest, the 170 pounds or 70 kilograms or whatever you happen to weigh, is electromagnetic forces and quantum fields creating the appearance, the feeling, the solid seeming reality of a body that is, at the deepest level, almost nothing at all. And here is the thought I want to leave you with as we prepare to move forward. We began tonight by talking about the emptiness of outer space. We travelled outward through scales of void so large that human language runs out of useful words before the distances run out. And now we have travelled inward, and we have found the same emptiness waiting for us there, at the smallest scales physics can currently probe. The universe is empty at the top and empty at the bottom, and the matter that fills the space between those extremes is itself mostly empty, held together by forces and fields into the semblance of solidity. We are not visitors to an empty universe, we are expressions of it. The void is not out there, somewhere between the stars separate from us and our solid familiar world. The void is in here, between every atom of every cell, between every quark in every proton. We are made of the same emptiness we have been contemplating all evening, and somehow, improbably, magnificently that emptiness thinks. In the summer of 1950, the physicist Enrico Fermi was walking to lunch with several colleagues at Los Alamos National Laboratory in New Mexico. The conversation had turned, as conversations among physicists sometimes do, to the subject of extraterrestrial intelligence. There had been a cartoon in a New York newspaper, recently depicting little green men stealing New York City's trash cans, and someone at the table made a joke about it. Fermi listened, and then, with the kind of sudden clarity that marks the genuinely original scientific mind, he asked a question so simple and so devastating that it has not been answered in the 75 years since he posed it. The question was this: if the universe is as old and as vast as we believe, and if the conditions for life are not unique to Earth, then where is everybody? It is 3 words in its shortest form: where is everybody? And it is, when you sit with it in the quiet, one of the most terrifying questions ever asked. Let me build the weight of the question carefully, because it is easy to hear it and nod and move on without feeling it properly. The observable universe contains roughly 2 trillion galaxies. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Astronomers now estimate that the majority of those stars host planetary systems, and that a significant fraction of those planets orbit within the habitable zone of their stars, the range of distances where liquid water could exist on a surface. The universe is 13.8 billion years old. Our own solar system is only 4.6 billion years old, which means that billions of star systems existed and had time to develop for billions of years before our sun even formed. If life arises wherever conditions permit, and if intelligent life eventually develops the capacity for communication and space travel, then the galaxy should be, by now, teeming with signals, with probes, with some evidence of the civilizations that should have had billions of years head start on us. The math on its face suggests that we should not be alone, and yet, the sky is silent. Completely, utterly, and so far as every instrument we have ever built can determine, absolutely silent. This silence has a name, the Great Silence, or more commonly the Fermi Paradox. and it connects to everything we've been discussing tonight in a way that I find both intellectually fascinating and genuinely quietly chilling. Because the emptiness of space, the vast, structured, overwhelming void we have been travelling through, is not just a physical fact. It may also be a biological fact. It may be telling us something about the rarity not just of matter, but of the particular kind of complexity that matter occasionally achieves. Life, mind, civilization. The emptiness of the cosmos may extend not just to atoms and galaxies, but to the phenomenon of awareness itself. We may be sitting in a void not just of matter, but of minds, and if that is true, then the loneliness it implies is of a different order entirely from the loneliness of empty space. There are many proposed solutions to the Fermi paradox, and I want to walk through several of them tonight because each one illuminates a different aspect of what the silence might mean. The first, and perhaps most straightforward, is simply distance. The universe is so vast and the speed of a light so finite that even a civilization broadcasting signals for millions of years might not have had those signals reach us yet. The Milky Way is 100,000 light-years across. A signal sent from the far side of the galaxy 100,000 years ago is only just arriving now. If civilizations are spread thinly enough across the galaxy, and if they have only been broadcasting for a geologically brief period, the silence might simply be a consequence of the scale of the void we have already described. We are not necessarily alone. We may simply be out of range, separated by the same emptiness that separates stars from each other, in a galaxy too large for any signal to have reliably crossed in the time available. The second solution is time. We have been capable of sending and receiving radio signals for roughly 100 years, 100 years out of 13.8 billion. If you compressed the age of the universe into a single calendar year, our radio-capable civilization has existed for less than a quarter of a second before midnight on December 31st. We are extraordinarily new. Any civilization that arose and developed and perhaps expanded and perhaps even declined before we were listening would have left signals that have long since passed through our corner of the galaxy and dispersed into the void, too faint now to detect. The silence may be the silence of a conversation we missed by arriving late. The universe may have been loud once, and we may simply have not been awake to hear it. The third solution is the one I find most unsettling, and it deserves to be spoken carefully. It is called the Great Filter. The idea, proposed by economist Robin Hanson in 1998, is that somewhere on the path from simple chemistry to galaxy-spanning civilization, there is a step so difficult, so improbable, so catastrophically hard to traverse that almost no lineage of life makes it through. A filter so fine that the universe, despite its age and its billions of potentially habitable worlds, has produced essentially no civilizations capable of making themselves known across interstellar distances. The terrifying question that the Great Filter poses is not just whether the filter exists, but where it sits. If the filter is behind us, if the hard step was something early in our history, like the origin of life or the development of the eukaryotic cell, or the emergence of multicellular organisms, then we may be genuinely rare, genuinely lucky, and the emptiness ahead of us may be ours to fill. But if the filter is ahead of us, if the step that almost no civilization survives is something that technologically advanced species inevitably encounter, then the silence of the sky is not merely lonely, it is a warning. I do not want to leave you in the dark with only dread, because the Fermi paradox has softer resolutions too, and honesty requires that I mention them. Perhaps intelligent life communicates in ways we have not yet thought to listen for. Perhaps civilizations turn inward rather than outward, building rich inner worlds of computation and experience rather than broadcasting into the void. Perhaps the universe is in an early phase, and we are among the first complex minds to arise, with billions of years of biological and civilizational development still ahead for the galaxy as a whole. Perhaps life is common but intelligence is rare, or intelligence is common but communication is rare, or communication is common but we are simply not yet sensitive enough to hear it. The silence admits many interpretations. What it does not admit is easy comfort. The night sky, when you really listen to it, is very, very quiet. And whether that quiet speaks of our rarity, our earliness, our limitations, or something darker and harder to name, it speaks with the same voice that has guided us all evening. The voice of an almost incomprehensibly empty universe, waiting to be understood. On Christmas Day of 2021, a rocket lifted off from a launch site in French Guiana, carrying the most complex and most expensive scientific instrument ever built. The James Webb Space Telescope, nearly 30 years in development, delayed repeatedly, revised fundamentally, assembled from contributions by thousands of scientists and engineers across multiple countries, unfolded itself over the following weeks in a sequence of deployments so intricate and so unforgiving that mission controllers described the process as containing over 300 single points of failure, any one of which could have ended the mission entirely. Sunshield panels the size of a tennis court had to unfurl correctly. A segmented primary mirror made of 18 gold-coated hexagonal sections had to align with nanometer precision in the cold of space. Everything had to work in the right order, a million miles from Earth, with no possibility of human repair. Everything did work, and when the telescope finally opened its eye and looked back through time, what it showed us was not a confirmation of what we expected. It was something stranger, more beautiful, and in the context of everything we have been discussing tonight, more humbling than almost anyone had prepared for. The James Webb Space Telescope was designed to see further back in time than any instrument before it. Because light travels at a finite speed, looking at distant objects is the same as looking at the past. The light from a galaxy 10 billion light-years away left that galaxy 10 billion years ago, and it is that ancient light, that 10 billion-year-old signal, that arrives at our telescopes today. Webb, operating in the infrared range of the electromagnetic spectrum, can detect light that has been stretched by the expansion of the universe during its long journey, light that began its crossing as ultraviolet or visible and has been redshifted by billions of years of cosmic expansion into the infrared, invisible to ordinary cameras but perfectly suited to Webb's detectors. This design allows Webb to peer into the first few 100 million years of cosmic history, a period astronomers call cosmic dawn, when the first stars and galaxies were lighting up the previously dark universe for the very first time. What Webb found in those first deep images stunned the astronomical community. The telescope was pointed at regions of sky that Hubble, Webb's predecessor, had shown to be essentially empty. Patches of darkness between visible objects, areas that previous observations suggested contained little of significance. And in those apparently empty patches, Webb found galaxies, thousands of them, ancient galaxies, formed within the first 500 million years of the universe's existence, far earlier and far more developed than current models of galaxy formation had predicted. Galaxies with mature structure, with what appeared to be established stellar populations, appearing at a time when the universe was too young, according to our best theories, to have produced such things. The early universe was not the gradual, gentle emergence of simple structures that cosmologists had modelled. Something was building galaxies faster, more efficiently and more extensively than our theories had room for. The emptiness between those galaxies was real and vast, but the galaxies themselves were arriving earlier and in greater numbers than the models predicted, and the questions their presence raises are ones we do not yet have answers for. One of the most profound images Webb has produced, and I want you to picture this clearly as I describe it, is what astronomers call a deep field image. Webb was pointed at a tiny patch of sky, roughly the size of a grain of sand held at arm's length, and exposed for many hours, collecting the most ancient light it could reach. The resulting image contains thousands of galaxies, each one a collection of billions of stars, each one separated from its neighbours by millions or billions of light-years of empty space. Some of those galaxies are so distant that the light we're seeing left them when the universe was less than 1 billion years old. We are looking at structures that formed before our Sun existed by more than 9 billion years, and between every galaxy in that image, in the dark spaces that separate one smear of ancient light from the next, there is the void we have been describing all evening, empty, cold, vast beyond measurement. The deep field images of Webb are not pictures of a crowded universe. They are pictures of islands of impossible complexity separated by oceans of absolute nothing, each island a different chapter in a history that began long before anything we would recognise as familiar. But Webb is not only looking backward, it is also transforming our understanding of the present and the intermediate past. Its observations of stellar nurseries, regions where new stars are currently forming inside dense clouds of gas and dust, have revealed structures of extraordinary detail that were previously hidden behind the dust itself. infrared light passes through dust where visible light cannot, and Webb's images of regions like the Carina Nebula and the Pillars of Creation show jets of material being ejected by newly forming protostars, bow shocks where those jets collide with surrounding gas, and delicate filaments of illuminated material stretching across light years of space. These images show star formation not as a smooth and gradual process, but as a turbulent, violent, and astonishingly dynamic one. And they show, even in the densest stellar nurseries, how much of the volume is still empty, still dark, still dominated by the void that makes even regions of active creation seem sparse by any human standard. Webb has also been examining the atmospheres of exoplanets, worlds orbiting other stars, with a precision that was previously impossible. By observing the light of a star as its planet passes in front of it, Webb can detect how different wavelengths of light are absorbed by the planet's atmosphere, revealing the chemical composition of air around worlds light years away. In 2023, Webb detected carbon dioxide and sulfur dioxide in the atmosphere of a planet called WASP-39b, a gas giant orbiting a star roughly 700 light-years from Earth. These are not signs of life, but they are proof that the chemistry of distant worlds is accessible to us now in ways it never was before. Every world Webb examines sits in its own bubble of emptiness, separated from us and from every other world by the same void we have been crossing all night. And yet, across that void, light carries information. Chemistry leaves fingerprints in starlight. The emptiness, for all its immensity, is not opaque. What Webb is ultimately revealing, in image after image and dataset after dataset, is a universe that is simultaneously more structured and more empty than we imagined. More structured because galaxies formed earlier and more extensively than our models predicted, because stellar nurseries are more dynamic and more complex than previous observations could show, because the chemistry of distant worlds is richer and more varied than we had evidence to confirm, and more empty because every new deep field image shows that between all those structures, between the galaxies, between the stellar nurseries, between the systems Webb is revealing to us one by one, the void persists. It is always there, in every image, in every gap between one point of light and the next. The darkness that surrounds every galaxy Webb has photographed is not a background. It is the dominant feature. It is the context in which all the light exists. Webb is showing us the universe more clearly than we have ever seen it, and the universe, seen clearly, is mostly dark. I want to take you somewhere tonight that very few people ever allow themselves to go. Not back in time to the Big Bang and the first moments of creation, but forward. Into the deep future. Into the cosmological long run, where the timescales involved make the 13.8 billion years of the universe's history so far look like the first breath of a very long night. Most of us live our lives bounded by human timescales. Days, years, decades, perhaps a century if we're fortunate. We extend our thinking occasionally to the scale of civilizations, to thousands of years of history, or to the geological timescales of millions of years that shape the continents and the fossil record. But the universe has a future that dwarfs all of these by factors so large that new words are almost needed. And what that future holds, if our current physics is correct, is a story not of growth and complexity and light, but of a slow, inexorable, extraordinarily patient return to something very close to nothing. Tonight, we follow that story to its end. The first phase of the deep future is already underway, and we have already described its engine: dark energy. The accelerating expansion of the universe, driven by that mysterious energy embedded in the fabric of space itself, is already pushing galaxies beyond our cosmic horizon. Galaxies that are currently visible to our best telescopes will, over the coming tens of billions of years, recede beyond the point where their light can ever reach us again. The observable universe, already vast almost beyond comprehension, will appear to shrink, not because it is actually smaller, but because the expansion of space will carry its distant contents permanently out of reach. Civilizations in the far future, if any exist, will look out at a sky containing far fewer galaxies than we can see today. The universe will appear lonelier. The evidence for the Big Bang itself, the ancient light of the cosmic microwave background, the distribution of galaxies across vast scales, will become harder and harder to read as the data recedes beyond any possible horizon. A civilization arising 1 trillion years from now might look out at a sky containing only their own galaxy, with no evidence that any other structure exists, and might reasonably conclude that their galaxy is all there is. The Sun has approximately 5 billion years of hydrogen fuel remaining in its core. In roughly 1 billion years, its increasing luminosity will make the surface of the Earth too hot for liquid water oceans, ending the conditions that have sustained life here for nearly 4 billion years. In about 5 billion years, the Sun will exhaust its core hydrogen, expand into a red giant large enough to engulf Mercury and Venus, and possibly the Earth itself, and then shed its outer layers as a planetary nebula before its core collapses into a white dwarf, a dense, Earth-sized remnant of stellar ash, cooling slowly over billions of years. This is the standard stellar endpoint for stars of the Sun's mass, and it will happen to the vast majority of stars in the Milky Way over the next several trillion years. The galaxy will not go dark all at once. It will dim gradually, as star after star exhausts its fuel and transitions from a burning fire to a cooling ember. The era of star formation will eventually end. The gas clouds that currently collapse to form new stars will be consumed, dispersed, or locked up in stellar remnants. Astronomers estimate that the last new stars will form somewhere in the range of 100 trillion years from now, 100 times the current age of the universe. After that point, no new fires will ignite. The existing stars will continue to burn, the longest lived of them, the cool, dim red dwarfs that sip their hydrogen fuel with extraordinary efficiency, persisting for trillions of years. But one by one, they too will exhaust their fuel. One by one, they will cool and darken. The Milky Way, which today blazes with the light of hundreds of billions of stars, will over these unimaginable timescales become a collection of cold, dark stellar remnants, white dwarfs cooling toward absolute zero, neutron stars spinning down their rotation, black holes sitting in the dark. This era, which cosmologists call the degenerate era, will last for an almost incomprehensible span of time, stretching from roughly 100 trillion years to perhaps 10 to the 37th power years from now, a number with 37 zeros, against which our current universe's age is not even a rounding error. And then, even the remnants begin to go. Protons, the fundamental building blocks of atomic nuclei, the particles that make up essentially all the ordinary matter we have discussed tonight, may not be stable forever. Current physics suggests, though has not yet confirmed, that protons have a finite lifetime, decaying over timescales of perhaps 10 to the 34th power years or longer. If proton decay is real, then all the white dwarfs and neutron stars and rocky planets and cold drifting asteroids that have survived the death of the stars will themselves dissolve, slowly and silently, their matter converting to lighter particles and radiation, until nothing made of ordinary matter remains anywhere in the universe. The stellar remnants will evaporate, the planets will dissolve, the last solid structures in the cosmos will come apart at the atomic level, not with violence or drama, but with the quiet inevitability of a physical law that has been waiting billions upon billions of years to finish its work. What remains after the degenerate era and the decay of all ordinary matter are the black holes. They are the last survivors, the densest concentrations of mass energy the universe ever produced, immune to the processes that dissolve ordinary matter, persisting in the dark long after everything else has gone cold and quiet. But even black holes are not eternal. Stephen Hawking demonstrated theoretically in 1974 that black holes slowly radiate energy through a quantum mechanical process now called Hawking radiation. The process is extraordinarily slow. A stellar mass black hole radiates so little energy that it would take roughly 10 to the 67th power years to evaporate completely, and a supermassive black hole at the centre of a galaxy might persist for 10 to the 100th power years or more. But evaporate it does, particle by particle, quantum by quantum, until nothing remains but a final burst of low-energy radiation, and then silence. The last black hole in the universe evaporates and there is nothing left. No matter, no structure, no light worth naming. Just an expanding, cooling, featureless sea of the lowest energy particles physics permits. A state cosmologists call the heat death of the universe, or maximum entropy. A condition of such perfect uniform sameness that nothing can ever happen again, because nothing can ever be different from anything else. I want to end this chapter not with despair, but with a kind of perspective that I find genuinely clarifying rather than crushing. All of this, the cooling stars, the dissolving planets, the evaporating black holes, the final silence, is not happening to us. It is happening to a universe that is right now in the extraordinary early bloom of its existence. We live in what cosmologists sometimes call the stelliferous era, the age of stars, a window of cosmic time during which the conditions for light and warmth and chemistry and life happen to coincide. We are not at the end of the story, we are very near its beginning. The universe, in its deep future, is heading toward emptiness. But right now, tonight, in this particular pocket of space and time, the stars are burning, the galaxies are spinning, the atoms in your body are arrayed in patterns complex enough to wonder about all of this. That is not nothing. In the context of what is coming, in the context of the vast cold silence that awaits the universe in its deep future, the fact that it is warm and bright and alive right now, that you are here, that any of this is happening at all, is the most improbable and most precious fact in a cosmos that will spend most of its existence as empty as the void we have been crossing all night. We have travelled a long way tonight. We began on the surface of a small planet, looking up at a night sky that felt full, and we have spent these hours slowly, carefully dismantling that feeling, not to replace it with despair, but to replace it with something more honest and I think more genuinely beautiful. We have crossed the solar system and found it mostly empty. We have pushed into the interstellar desert and found a near-perfect vacuum, cold beyond any human experience, stretching for light years in every direction. We've pulled back to the scale of galaxies and found them separated by abysses so vast that even the word emptiness stops feeling adequate. We have looked at the universe's inventory and found that everything we can see, every star, every galaxy, every atom of matter, adds up to 5% of what actually exists, with the rest being darkness and mystery. We have looked inward to the atom and found the same emptiness there, mirrored in the very matter we are made of. And we have looked forward into the deep future and found the universe moving, with dark and patient certainty, toward a final and total silence. That is the territory we have covered, and now I want to tell you what I think it means. There is a phrase that has been passed through the community of scientists and philosophers who think seriously about the cosmos, and it belongs most famously to the astronomer Carl Sagan. Though versions of the idea have surfaced in many minds across many generations, the phrase is this: we are a way for the cosmos to know itself, or as I prefer to say it tonight, in the quiet we have built together over these hours, we are the universe noticing itself. I want to stay with those words because I think they contain something that the long journey we have taken tonight makes visible in a way that cannot be accessed any other way. When you look up at the night sky and feel wonder, that specific particular feeling of smallness combined with connection, of being dwarfed and yet somehow included, you are not a human being looking at the universe from outside it. You are the universe looking at itself from inside. You are the part of the cosmos that has become complex enough to be curious about the rest. Consider what had to happen for this moment to be possible. 13.8 billion years ago, the universe began in a state of near-perfect uniformity. Hot, dense, and containing almost nothing that we would recognize. The 1 in a billion asymmetry between matter and antimatter saved a thin surplus of matter from annihilation. Quantum fluctuations seeded the first density variations. Dark matter provided the invisible scaffolding on which those variations grew. Gravity amplified the dense regions over hundreds of millions of years until the first stars ignited in the darkness. Those first stars burned through their hydrogen and exploded as supernovae, seeding the surrounding gas with carbon, oxygen, nitrogen, iron, all the elements that hydrogen and helium alone cannot produce. Later generations of stars incorporated those heavier elements, building planetary systems around themselves, including one particular system, unremarkable by stellar standards, that formed 4.6 billion years ago in an outer arm of a spiral galaxy we call the Milky Way. On the third planet of that system, liquid water pooled in the lowlands. Chemistry happened in that water, slowly and then more quickly, until something crossed the threshold from reaction to replication, from chemistry to biology. And over the next 4 billion years, that biology grew more complex, branched into millions of forms, tried and failed and adapted and persisted, until one lineage developed a nervous system capable of abstract thought, language, mathematics, and wonder. And that lineage, on a particular evening, lay down in the dark and listened to someone describe the emptiness of the universe and felt something. That chain of events, from the Big Bang to the asymmetry to the first stars to the supernovae to the solar system to the ocean, to the cell to the nervous system to this moment, is so long and so improbable at each step that the mind genuinely staggers when it tries to follow it all the way, and yet it happened. It is happening right now, in you, as you process these words and hold these images and feel whatever it is you are feeling as the night deepens around you. The universe spent 13.8 billion years building the conditions for this. It built them without intention, without plan, through the operation of physical laws that had no preference for the outcome, and yet the outcome is this: matter that knows it exists, energy organized into the shape of a question, the cosmos, which is almost entirely empty and mostly dark and heading toward a final silence, briefly, improbably, magnificently, aware of itself. I want to say something about the emptiness now that I hope lands differently than it might have at the start of tonight. The void that we have been describing, the interstellar desert, the intergalactic abyss, the dark matter halo, the expanding nothing, is not our enemy. It is not a rebuke to our existence or a measure of our insignificance. It is the context without which we could not be here. Stars need space to form. Galaxies need the void to develop their structure. The universe needs room to expand and cool, from its initial extreme into the gentle temperature ranges where chemistry is possible and biology can emerge. The emptiness is not the opposite of life, it is the condition for it. Without the void, there is no room for complexity. Without the silence, there is no possibility of the note. We exist not despite the emptiness, but because of it. We are what the emptiness made, in the one place and time where the conditions aligned, from the rounding error of matter that survived the beginning. And so as tonight ends, and as you prepare to let sleep take you, I want to offer you not a resolution to the paradox we began with. Why is space so empty when there is so much in it, but a reframing of it? The question assumes that emptiness and abundance are opposites, that a universe containing so much should not also be so empty. But perhaps they are not opposites. Perhaps the emptiness and the abundance are the same thing seen from two different scales. At the scale of the cosmos, the universe is almost nothing, a thin tracing of matter on the surface of an incomprehensible void. At the scale of a planet, of an ocean, of a cell, of a mind, that thin tracing becomes everything. Every atom of you is a product of stellar nucleosynthesis, cosmic violence, geological time, and biological patience. You are, in the most literal physical sense, made of the universe's rarest and most precious product. You are the part of almost nothing that became something. You are the local exception to a rule that holds almost everywhere else, and you are awake, tonight, in the dark, thinking about it. That is not nothing. That is, in fact, everything. Thank you for staying with me through all of this. Thank you for making the journey, from our solar system outward to the cosmic web, inward to the atom, forward to the deep future, and back again to this moment, this night, this small, warm place in a vast, cold universe. If tonight gave you something to carry, a sense of scale, a feeling of improbable belonging, a new way of looking at the darkness between the stars, then please consider sharing it by liking this exploration or subscribing so we can keep making these journeys together. It is a small thing, but it helps more minds find their way to these questions, and these questions deserve all the company they can get. The next time you step outside on a clear night and look up, I hope you see something different than you did before. Not just stars, but the improbable islands they are. Not just darkness, but the void that made room for everything. Not just a sky, but a mirror. Sleep well tonight. Keep looking up at the stars, and remember, the universe spent 13.8 billion years becoming something that could notice itself. Tonight, it did. Good night.